This screen looks dark, but by looking through these glasses you can definitely tell it's on. However, tilting the glasses back horizontally and it no longer works. There's no CGI here, so what's going on? Well, the key has to do with polarization and the fact that I snuck an extra polarized lens in front of the camera while you were scrolling a few videos ago. To understand what's going on, I'm going to use this spring to represent light and this foam cut out of sunglasses to visualize polarized lenses. Shout out to Seraph Secure for making this video possible, more about them later. You can think of a polarized filter as having a bunch of slits that let light pass through. In this example, the slits were made vertically to indicate vertical polarization, which is the direction that sunglasses are polarized. Light travels in waves and can travel in any direction. A vertically traveling light wave, so to speak, looks like this. It moves up and down as it travels across the room. While a horizontal one looks like this, it moves side to side. After feeding the spring through my model sunglasses, you can now see that waves traveling vertically can pass through the sunglasses. However, waves traveling horizontally will not make it through and get blocked. So having one lens in front of a light source only blocks out some of the light so that it looks dimmer. But if you place a second lens and rotate it such that it's perpendicular to the first, then at least in theory with perfect lenses, it blocks out all light. The vertical light that can make it through the first lens can't make it through the second one since it's perpendicular, and you can see it here again in slow motion. That all makes some sense, but if you're like me, you might have been surprised to learn that even if you have two perpendicular polarized lenses, you can place a third one in between the two and rotate it at an angle, and light once again makes it through. This clip was from my Two Truths and Trash episode, and spoiler, it absolutely is real. A reason this might be surprising though is because we only did the spring and slits visualization for waves traveling parallel or perpendicular to the slits. However, as mentioned, waves don't just travel in these two directions, but rather can travel at any random angle, like this one for example. Since waves are difficult to see when looking straight at them, I'll just draw a vector with an arrow like this to show the amplitude and direction of these waves. So a vertical one would have a vector like this, a horizontal one would have a vector like this, and if it's at some angle like this one, it would be drawn at whatever angle it's at. It makes sense that a wave traveling parallel to the slits can completely pass through, while a wave traveling perpendicular is completely blocked. But for a wave traveling at some angle in between, you can simply take this vector and separate it into components that are parallel and perpendicular to the slits. Now, as you probably could guess, the component shown in green, which is traveling parallel to the slits, can make it through, while the component shown in red is perpendicular to the slits, meaning it gets blocked. As a result, some does get through, but it's less than if the entire thing was parallel. Light from a flashlight or the sun is unpolarized light, meaning it's traveling in all sorts of directions. Since this is an absolute mess to visualize, I'll once again represent each ray of light in this beam with a vector showing its direction and strength. So when this random collection of light rays passes through a single polarized lens and you do the vector math, letting only the parallel components through, some of the light did get blocked so it's dimmer, and now all the light that's remaining is vertically polarized. Since the unpolarized light vectors all have random directions, a single lens will block out the same amount of light on average no matter the direction. But sunglasses are still specifically designed to have vertical polarization for a good reason. When unpolarized light is at a low angle relative to a smooth surface like this table, some of that light gets reflected off the surface and produces an annoying glare. If I look at this glare with glasses on the wrong way, it doesn't do much. However, if I rotate them back to normal, the glare is almost entirely removed. That's because when unpolarized light hits a smooth surface, some of that reflected light becomes partially polarized in a direction parallel to that surface. So this table is horizontal, and the horizontal slits would let it through, while vertical ones would not. Most surfaces aren't this smooth and they're not always horizontal relative to you, but it's still worth having, especially if you're near still water swamps with alligator infested waters. Anyway, with the basics already covered, let's head back to the 3-lens example, but first you need to know that monitors also have a polarized filter in front of the screen. So you can do the same 2-lens trick to block out all light, depending on which way the monitor is rotated of course, and I thought this was interesting, but not all my monitors were polarized in the same way. It's also worth noting that phone screens are polarized too. And as shown with the red arrow, mine was polarized at an angle, so I needed the sunglasses perpendicular to that to block out the light. Knowing that at some angle the screen should go dark is a great life hack to make sure sunglasses that you find at the store are polarized before purchasing them, especially if you're buying them secondhand, as it can help you avoid getting scammed. Speaking of helping you avoid scams, the YouTuber Kit Boga, who you might know for wasting scammers' time,
Sorry, I'm not very good with the computers.
well, he founded a software company called Seraph Secure that helps prevent scams. Back in college, my grandma was told by a scammer that I was arrested, put in jail, and she needed to give money immediately to bail me out. My grandma was convinced, but luckily she thought to call my mom first, and my mom assured her that I was probably not in jail and that she should not send the money. I was in fact not in jail, so thankfully the scammer received nothing, but all too often the elderly are susceptible to these awful scams. That's why I think Seraph Secure's notification system is so smart. You can set it up so that if something suspicious is happening on your loved one's computer, you can get notified and step in to be the hero. Seraph Secure also blocks over 100,000 phishing and scam websites. Those features are in the premium version, but there's also a completely free version that lets you scan your computer to see if there's any remote control software that's been installed. This software is often used by scammers to take control of your computer to gain access to your financial information, your emails, or even your webcam. Seraph Secure lets you easily remove any of this type of software that's been detected, and it also helps prevent you from installing new ones in the future. If you're interested in trying them out, you can go to seraphsecure.com/science. Thanks so much for your support, and now back to your regularly scheduled program. As discussed, when unpolarized light passes through that first filter, some of the light gets blocked, and the remaining light that does make it through is now vertically polarized. If the lens immediately after was horizontal, then all this vertically polarized light would be perpendicular to those slits, meaning it would all get blocked and you wouldn't see anything. However, if that vertical light first passed through a filter tilted at an angle, only some of the light would be blocked and the parallel components would once again make it through. Now the remaining light is traveling at a new angle and it's no longer perpendicular to the horizontal slits at the end. So once again, splitting the vectors into parallel and perpendicular components and only letting the parallel through, and you see that light has successfully made it through all three lenses. This scenario is exactly what was happening in both of the examples I showed earlier. That first polarized filter is on the monitor itself. Then the third lens is placed directly in front of the camera, making sure it's perpendicular so that in theory all the light is blocked. Then that middle angled lens is either taped there or I'm holding it and rotating it to be about 45 degrees. 45 degrees lets the most light through, sort of like it's a compromise between the two perpendicular lenses on the ends. However, you can keep adding more lenses in between to make the transition more gradual, so to speak. And each time you add one like this, more light makes it through, although it's definitely non-linear. I'm going to try this with a bunch of filters to see how much light from this laser can pass through, but I have to point out one last thing that I've been ignoring for simplicity, which is that these vectors I've been drawing are actually representing the electric field of the light wave, not the intensity. So the electric field vector before times cosine of the angle to get the parallel component will equal the electric field after. Since we care more about the intensity than the electric field, we can convert this equation by using the fact that the intensity of light is proportional to the square of the electric field. So squaring both sides and plugging in the intensity, and you get the final equation that tells us how much light intensity would theoretically make it through. And this equation is known as Malice's law. So it's not multiplied by cosine of the angle, but cosine squared of the angle. If this part was confusing to you, don't worry about it too much, and that's why I didn't bring it up earlier. Anyway, I felt like I needed to add that part, but let's move on with trying a bunch of lenses in real life. Here's what the laser looks like when it passes through one lens, and now I'm adding a perpendicular one, so this is the darkest it will be. This time I added them one at a time, starting from the back, and the first couple definitely made the largest difference. As I kept going, the intensity did seem to increase, although it wasn't quite as noticeable, and for the last couple, it was definitely hard to tell whether it even worked at all. At some point, it seems like the lens imperfections would outweigh the benefit, or it has to do with the fact that I taped these filters to some clear acrylic, just so that it was rigid. The way humans perceive brightness also isn't the same as intensity, so that could be another reason, or it's just something I'm not considering, so let me know in the comments. I tried my best in this video to simplify things as much as possible, and while the vectors can work to explain what's going on, don't forget that this is ignoring what's actually happening to light on a quantum level. With that said, hopefully you learned something in this video. Thanks for watching to the end, and I'll see you next time.